Dungeons & Dragons has a game mechanic where you roll a 20-sided dice 2 times and you take the maximum of those 2 rolls. This is called rolling with advantage because you have 2 chances for a high roll to come up. But how much higher is it really? Well, you can calculate that on average, this maximum is 13.825. This is about 3.3 higher than the ordinary average of a 20-sided dice, which is 10.5. Now, the generalized version of this is to ask, what happens if you roll an n-sided dice m times? What is the average maximum of this collection of m dice rolls? How does it depend on the number of sides n and the number of times you rolled it m? And this problem was the subject of a stand-up maths video exactly on this topic. In that video, Matt Parker calculated the average maximum for small values of m using sums, and then used computer simulations to come up with this conjecture of what's going on for every value of n and m. Let's take a look.
So my conjecture is, it's always, for m dice rolled with advantage, it's m divided by m plus 1 times n plus a half.
So for example, in the ordinary D&D case where m equals 2, this factor in front, m over m plus 1, is 2/3. So you get 2/3 times 20 plus a half. 2/3 times 20 is 13.333 plus a half, 13.83. So it's pretty close to the right answer. It's an overestimate by about 0.01.
Feel free to prove, disprove, or extend my conjecture.
In this video, I'm going to prove Matt's conjecture, and I'm going to improve on it in 2 ways. The first way is I'm going to add a term to the end. So Matt had this conjecture of the first 2 terms, m over m plus 1 times n plus a half, and I'm adding on one more term, which is minus m over 12n. And to see how good this is, let's take a look at some graphs of the error size of these different estimates. So in this diagram, I have n, which is the number of sides on the dice, ranging all the way from 6 up to 20. So going from left to right, we have more and more sides on the dice. And on the y-axis, I'm plotting the error size. So this is how close is the true average maximum? How close is it to this approximation that we've come up with? And I've plotted 2 things on here. There is the 3-term approximation. That's my approximation with all 3 terms. And there's the 2-term approximation. That's just these first 2 terms. And that is exactly what Matt Parker came up with. So let's see how close these approximations are. So the 2-term approximations are exactly these dashed lines over here. And I have various values of m plotted in the different colors. So m equals 2 is this first line over here. That's the classic D&D setup. Roll 2 dice, take the maximum. And you can see the error size is indeed going down to 0. So Matt Parker's formula is correct. As you increase the number of sides on the dice, this formula gets more and more accurate, and the error is going to 0. So for a 20-sided dice, you're off by about 0.01. Pretty good approximation. The thing is, as you roll more and more dice, the errors get worse. So if you roll 7 dice and take the maximum, that's m equals 7 all the way up here, then the error is much bigger. It's like 0.04. So the error is going to 0, but it can be a little bit large even for a 20-sided dice if you roll enough dice. On the other hand, if you include this 3rd term, that's my term that I'm going to do in this video, then you get the errors that are down here. So these errors are so close to 0 that you can barely see them here. Let's zoom in a little bit and take a look. And now we've zoomed right in. So you can see the scale for the error size has now changed. Now instead of being 0.01, it's like 0.0001. So we have 3 zeros and then a 1. And so including this extra term makes the error size in this approximation phenomenally small. So the punchline is that this 3rd term really improves the error quite a lot. You get an extremely accurate approximation. And the other thing I'm going to do that's different than what Matt Parker did is I'm going to do what I call a probability ninja proof. So in probability, a lot of times you can get the right answer by just cranking out the formulas, get those probabilities, add them up in the right way, get the answer. But there's often a secret other way you can approach the problem. You kind of like look at the problem from the right way, you kind of manipulate the random variables in the right weird ways, and the solution will just fall out without having to do any calculation. And I kind of think of this like a ninja. It's like you sneak into the problem and just like hit it the right way and the answers will fall out. And when you do this, you get a lot of nice formulas and you kind of get a nice intuition of where things are coming from. So for example, this factor of m over m plus 1, we're going to see that this is a nice symmetry property of uniform random variables. So when you roll a dice or take a uniform random variable, you sort of have this symmetry of choosing all the things equally likely. And this m over m plus 1 is going to be exactly because we're going to have m plus 1 segments and we're going to choose m of them. So in this little diagram over here, I have m equals 3 as an example. There's going to be 4 segments on a circle, and we're going to pick 3 of them. That's where m over m plus 1 is going to come from. Similarly, the +1/2, it's going to be related to rounding errors. So we're going to see that when we are calculating this thing, we're always rounding our dice rolls in a certain way, and that's going to lead to this average of a half. That's the average amount of rounding we're going to have to do. And last but not least, this final term, it is related to the birthday paradox. This is everybody's favorite probability problem. And using calculations from the birthday paradox, we're going to calculate this minus m over 12n. All right, now one of the hardest things about this problem is not mixing up which one is n and which one is m. So n, remember, is the number of sides per dice. M is the number of dice we're rolling and then taking the maximum of. I'm color coding them in blue and orange. And I'm also going to keep down here, I'm going to keep a little bank of all the definitions that we need so we don't forget. If you ever get confused, pause the video and check it out. Here's another notation I'm going to use. I'm going to say x is a dice roll from 1 to n. That's an n-sided dice roll. And instead of writing average maximum, I'm going to write it mathematically in terms of these x's as the expected value. That's what that funny e symbol means. And I'm going to do maximum of x1, x2, ... all the way up to xm. So we have a collection of m of these dice rolls, n independent dice rolls, and we're taking the maximum and then taking the average. And by writing things out this way, we're going to be able to do manipulations inside the brackets. So for example, let's say we wanted to calculate not the maximum, but the expected minimum. That would look like this. And now we can do a nice trick that converts the maximum into the minimum. For a dice roll x, it has the property that x is actually the same distribution as n plus 1 minus x. Actually, when you roll a real dice, you might notice that opposite sides of the dice always sum up to n plus 1. So if you roll a 6-sided dice, the opposite sides always add up to 7. So what this is saying is you can either roll the dice or you can roll the dice and then flip it over. That's still a fair dice roll. And when you take this property, n plus 1 minus x is still a fair dice roll, you can replace every individual copy of the x in here with their n plus 1 minus versions. And now you have a minimum where n plus 1 appears in every single term. And if n plus 1 appears in every single term, you can just pull that out as a constant. So the expected value of the minimum is the same as n plus 1 plus the expected value of negative all the x's. And here's the nice thing. The minimum of negative values is the same as maximum of the original values. If you want to find out which one is the smallest negative number, just take the biggest number. So this formula, we've effectively converted the expected value of the minimum into the expected value of the maximum, and they're related by just doing n plus 1 minus. So the same rule that works for the individual dice rolls works to convert the maximum into the minimum. And now, of course, if we have an approximation for the maximum, we can plug that in and get an approximation for the minimum. This approximation looks very similar to our maximum approximation. It's 1 over m plus 1 times n plus a half plus m over 12n. And this one is actually extra exciting because it turns out you can write the minimum in a very nice way. The minimum is exactly equal to, on average, it's equal to this sum of powers. So you do the sum of the integers 1 plus 2 plus 3 plus all the way up to n, all to the power m, and you divide it by n to the m, that will be exactly the expected value of the minimum. So in Matt Parker's video, he was using formulas like this, taking the sum and trying to work out what is the expected value of the minimum. In this video, we're doing the opposite, right? We have a probability ninja proof that's going to give us this approximation, and we can work it backwards. So if we know that the expected value of the minimum is approximately so and so much, we can effectively get an approximation for what is the sum of the first n integers to the power m. So we're gonna, sort of as a side effect of what we're doing, we're proving this formula for the sum of the powers. This is called Faulhaber's sum of powers formula. Well, okay, more accurately, Faulhaber's formula is for the entire sum. We have the first 3 terms of the approximation. Normally, this stuff is very complicated. You got to use Bernoulli numbers, and there's a whole bunch of weird stuff. I'll link a number file video on this topic. And I've never seen a nice probability proof of this thing, so I really like it for that. Okay, so let's start proving the formula. And we have 3 terms to do. We're going to do them one at a time, starting with term 1, then term 2, then term 3. And every time we're going to do it, it's like peeling into an onion layer by layer. We're going to get deeper into it and see what comes out. So the first thing we're going to do is what I call the 1-term approximation. And that's just very simply the average maximum is approximately proportional to n. It's m over m plus 1 times n. Now, why does this one come out? Well, the way this approximation is going to go is we're going to approximate our dice roll. So x is a dice roll. We're going to approximate it by something else, which I call u. U here is a uniform random variable. You might think this is very alien, but if you have a calculator, you probably have one of these u's floating around. Most calculators have a little rand button, and when you press it, you get a random number between 0 and 1. And what this approximation is saying is, look, instead of rolling a dice, so suppose you show up at your D&D game and you forgot your 20-sided dice, what you can do instead is get your calculator out, calculate u by hitting the rand button, and then multiply it by n. So for a 20-sided dice, you multiply it by 20. Here, let's see what I get when I do it. So here I go. If I ask my calculator for a random number, it gave me 0.812. And if I multiply that by 20, then I got 16.24. So it's saying rolling a dice, instead of rolling it, you can approximate it by doing this whole operation. And we can also see visually why this is. So if you imagine a regular dice roll, you can imagine the number line. If it's a 6-sided dice, it has a sort of little atom at the numbers 1, 2, 3, 4, 5, and 6. These all have probability 1/6. A 1/6 chance of being 1, a 1/6 chance of being 2, and so on. On the other hand, what is n times u? Well, u is a random variable which is sort of smooshed evenly between 0 and 1. So it's sort of like a continuum of all the possibilities between 0 and 1. It's sort of this area between 0 and 1. That's u. What is n times u? Well, when you multiply by n, you sort of stretch the entire thing out to the number line 0 to n. So n times u is evenly smooshed from 0 to 6, whereas x is these masses at 1, 2, 3, 4, 5, and 6. So this approximation is very much like if you think of something like a screwdriver, it's made of millions and millions of atoms, but normally you don't think of those atoms. You just think it's a continuum of metal that goes from one end to the other end. N times u is a continuum of probability going from 0 to 6, whereas x has atoms at 1, 2, 3, 4, 5, 6. But as you add more and more atoms, they get closer and closer together. These two things are approximately equal. All right, now why is this helpful for us? Well, if we want to do the maximum of x's of dice rolls, we can just take this approximation and apply the maximum operation to it. So on one side, we get x1, x2, x3 all the way up to xm. On the other side, we get nu1, nu2 all the way up to num. If x is approximately nu, then these two sequences of random variables should also be approximately equal to each other in some sense. So now we take the maximum, and here is the nice thing. On the right-hand side of the equation, we're multiplying every single term by n. So the factor of n is appearing in every single term, and that means we can pull it out of the maximum. So what we've done is we've effectively isolated the dependence on n as a multiplicative factor on the right-hand side. This is on the left-hand side, it's much harder to do that. The n's are all baked into the random variables, you can't pull the n out, but on the right-hand side you can. Now when you take the average, you do the average of both sides. The left-hand side is the average maximum that we want. The right-hand side has this factor of n. That factor of n can get pulled out even more, and now we just end up with the expected maximum of uniform random variables. So really the big advantage of what we've done is we have somehow eliminated the dependence on n. We've sucked that n out to the outside, and now we just have this problem. How do we deal with these maximum of uniform random variables? It turns out this is a very nice thing to do. The expected value of the maximum of uniforms is exactly m over m plus 1. This is not an approximation, this is exactly equal, and we will see a very nice symmetry reason why this is true. But once you know this is true, then you get the formula we wanted. The expected value of the maximum of dice rolls is approximately m over m plus 1 times n, and that's because you can approximate each dice roll by n times a uniform. All right, and let's focus now on this maximum of these uniforms. And to prove this thing, we're gonna do it in the case where m equals 3, and I promise you that everything will be exactly the same for the general m. We'll get back to that right at the end, but it's really nice to visualize with a concrete m equals 3 here. We're trying to prove that the expected maximum of 3 uniform random variables is 3/4. And actually, this kind of thing was the topic of a different stand-up maths video, where Matt Parker was taking the maximum of uniform random variables and trying to figure out why it's the same as other weird combinations of uniform random variables. So one way you can do this problem is you can figure out that the maximum of u1, u2, u3 is actually the same distribution as taking a single u to the power 1/3. Okay, very funny thing you can do. And then this average will be the same as that average. And now you can do this average by doing some nasty integral, and then it's the integral of u to the 1/3, and that is going to work out to the 3/4 that we want. But I promised you that I would do a probability ninja proof. So this kind of thing, this is not the way of the probability ninja. We're going to do it a different way by just looking at the random variable itself. And we'll see that this generalizes in a way that doing that integral does not. So here's how we're going to do it. We're going to take the maximum of u1, u2, u3. We're again going to think of a number line, now going from 0 to 1. And each of u1, u2, u3 is sort of a random point somewhere on this number line. You can draw them as 3 little dots. So there's u1, there's u2, and here comes u3. All right, very good. What is the maximum? Well, the maximum is just whichever one is furthest to the right. In this case, I think it was u2, but it doesn't matter which one it is. Once you draw the 3 dots down, the maximum is whichever dot is furthest to the right. And here's the perspective shift that will let you understand what this thing is on average in a really nice way. is instead of thinking of this as where is the third dot, what you should look at is the spaces between the dots. And the maximum is the third dot, yes, but it's also what you would get by adding up these little segments that are made in between. So don't think of the locations of the dots, think of the spaces between the dots as the random variables. We got an S1, the first segment, S2, the second segment, and S3, the third segment, and the maximum is literally just the sum of these three things. S1 plus S2 plus S3. And you might correctly notice S1, S2, and S3, they are a nasty combination, right? They depend on each other in some weird way. Maybe they're not very simple. But the nice thing is we've taken our problem, which used to have a maximum in it, and we've replaced it with a plus. And the nice thing about pluses is that averages play very nice with pluses. So if you take the average of the maximum, that's the average of S1 plus S2 plus S3, but you can take the average of each one individually. So the average is a linear, it's the expected value of S1 plus the expected value of S2 plus the expected value of S3. Now the dependence of S1, S2, and S3 don't matter to us, we just need to know how big is each of these on average. Here's where symmetry comes in. I claim that S1, S2, and S3 all have the exact same average. So it looks like maybe they're a little different. S1 is on the end, S2 is in the middle, but actually you can see that S1, S2, and S3 all have to have the exact same distribution individually. And you can see that very easily by taking this number line from 0 to 1 and wrapping it around a circle. So let's do that. Let's wrap S1, S2, and S3 around a circle. And you can see that when you have S1, S2, S3, and S4, they are sort of like you take 4 random points around the circle, and the segments S1, S2, S3, and S4 are the 4 segments made by these 4 random points. But when you take the 4 segments of a circle from 4 random points, there's no reason that it should go S1, S2, S3, S4. It could have equally well, with the same exact probability of occurring, it could have gone S4, S1, S2, S3, right? It's sort of equally likely that this configuration would come out. Very technically, to prove this, you would use a probability preserving map, which just shifts everything by 1. But the point is that S1, S2, S3, and S4, they are cyclically symmetric. So S1 and S2, they have the same distribution because you can rotate the circle to map S1 into S2. And because of that, they must all have the same exact average. So the thing we're looking for, expected value of S1 plus expected value of S2 plus expected value of S3, is simply 3 times the expected value of S1. It's the same thing added up 3 times. That's why there's going to be a 3 that appears. And how are we going to find the expected value of S1? We're going to use a nice trick. Notice you got S1, S2, S3, and S4. There's 4 segments around the circle. Altogether, these 4 segments are always equal to 1. They're the entire interval from 0 to 1. And so on average, they're also equal to 1. And that means that 4 times the expected value of S1 is equal to 1. All these segments have the same average, and together they make the whole circle. So that's 4 times the expected value of S1 equals 1. In other words, S1 equals a quarter. And if you take that and you plug it back in to what we wanted, then you get our answer that we were looking for. The expected value of the maximum of 3 random variables is 3/4. And of course, this idea, it generalizes very well. It works for any value of m. You're always going to get m plus 1 segments around the circle, and the maximum is always going to be m of them. But even more generally, you can do this argument not just for the maximum, but for the kth largest. So for example, what if you take, like the second largest item in a group of things? So you take U1 to UM and you say, please give me the second largest one. If k equals 2, that's the second largest. So looking at the kth largest dot from the right, and that is always equal to the sum of the first k segments. So in this case, S1 plus S2, that will give you the kth largest of all these things. And by linearity again, all these things are the same average. That is k times the average of any individual segment. And once again, because all the segments together add up to 1, that is k over m plus 1. So we've proven in this very general fact that the expected value of the kth largest of a bunch of things is k over m plus 1. And the k is there because you have k of these segments, and the m plus 1 is there because there's m plus 1 total segments to pick from. Now this random variable turns out has a name. It's called a beta random variable, and it has some parameters that depend on k and m. And normally when people do this thing, they do these crazy integrals. Like they have integrals that look like this, and they try to integrate this whole thing. It's a big mess. Every statistics textbook I've seen does these crazy integrals to prove that the average of a beta is k over m plus 1. But it's just a nice picture proof with symmetry and everything. I love this way of thinking about problems with pictures and seeing what's the intuition behind the k, what's the intuition behind the m plus 1. Anyway, for us, this proves it, and we're on to term 2. All right, the 2-term approximation, we have exactly what we had before, but this time we're adding on 1/2. So where does this plus 1/2 come from? And it comes from refining our approximation. So before we said x is approximately n times u, but can we do better than that, than just saying approximately? Well, yes, we can. One way is you can round up. So if you take n times u and you round it up, that will be exactly equal to x. And when I say equal, I mean equal in distribution. And what this is telling you is if you show up at your D&D party and you have forgotten your dice, then not only can you use your calculator to get a good approximation, you can sort of indistinguishably pretend to have a 20-sided dice by always rounding up whatever you get. So let's see, if I take a random number here, I got 0.734 as my random number. I multiply it by 20 to give me 14.68, and I gotta round that up, so it's like I rolled a 15 on my dice. And as long as I do this operation, I'm always rounding up, I will always get a number that is either 1 or 2 or 3 all the way up to 20, and it is indistinguishable from a fair dice roll. So this is how your calculator can save you when you go to a D&D party. So this is perfectly true, and it turns out it's more useful for us to write this thing in a slightly different way, which is instead of rounding up the right-hand side, we're going to sort of fake round down the left-hand side. So what I mean is we're gonna replace the rounding, we're not gonna do any rounding, and instead we're gonna subtract off some random amount I call delta. Delta stands for difference from the left-hand side. So now again, x is an integer, delta is gonna be a uniform random variable, and we're gonna take our dice roll and we're gonna subtract off a uniform amount. So this is like, you show up at your Dungeons & Dragons party with your 20-sided dice, you roll the dice, and I got 4, and now I subtract off something from my calculator. So now I'm gonna subtract off whatever I get here. I got 0.291, so I take 4 minus 0.291, that's the left-hand side over here, it is 3.719. And 3.719 is exactly the same as in distribution as doing the operation on the right-hand side of getting a random number between 0 and 20. So this is kind of the opposite, where instead of rounding up the right-hand side, we're sort of doing a reverse rounding of the left-hand side where we're subtracting off a little bit, and that little bit I'm calling delta. So I'll explain with a picture why this is true in the first place, but to see why this helps us, we're kind of subtracting something from the left-hand side. If we take our approximation that we want to prove, you can also write it as subtracting a half from the left-hand side. And you'll see this is exactly how it's going to come out. So this effect of subtracting off a little rounding error is exactly going to give that factor of a half in the approximation. Okay, why is this x minus delta equals n times u thing true? Let's draw a picture. So here's a number line for x, right? I'm drawing it from 0 to 6 just as an example. And x again is a little atom of size 1/6 at 1, 2, 3, all the way up to 6. What about delta? Well, minus delta is some random number between -1 and 0. So minus delta is represented by this little region of area between -1 and 0. And if you want to combine x and delta, so if you do x minus delta, where x and delta are two independent things, then you're doing what is called a convolution. And 3 Blue on Brown has a bunch of excellent videos on convolutions, but really what you're doing is you're kind of sliding this minus delta over to all the possible places it could be on the x and combining them. So for example, if you rolled a 1 on the x, right, to get x minus delta, then the effect of minus delta when you roll a 1 is to take that atom at 1 and spread it out between 0 and 1. So every time you roll a 1 on the dice, then when you subtract minus delta, you get something between 0 and 1 by taking this -1, 0 and subtracting off that 1. If you roll a 2, 3, 4, 5, or 6, each of those is going to, again, be spread out into the whole interval below it. So 2 gets spread out between 1 and 2, 3 gets spread out between 2 and 3, 4 gets spread out between 3 and 4, 5 gets spread out between 4 and 5, and 6 gets spread out between 5 and 6. And altogether, after you've done this subtraction, you have a nice interval that is all the way covered from 0 to n, and all the region is sort of equally spread out between this whole region. And so that is exactly what we had before. U was between 0 and 1, n times u was equally spread out between everything. X minus delta is exactly the same thing as n times u. They're both spreading out the region 0 to n equally likely. This is called a uniform random variable or a continuous uniform random variable. Okay, so this proves what we wanted. Now when we take the maximum of the left-hand side and the right-hand side, we're gonna have a bunch of dopey deltas sitting around. So we write out m copies of the left-hand side, and we do m copies of the right-hand side, and now we take the maximum of both sides, and we see that on the right-hand side, it's exactly what we did before, n times the maximum. We know on average, this is m over m plus 1. The right-hand side is unchanged from what we did before, and the only thing that's different is on the left-hand side, we have all these silly little deltas sitting inside. And we gotta find a way to pull these deltas out, and fortunately for us, it's not that bad. So to see what happens here, let's look at an example. So let's say that there were 3 dice rolls, m equals 3, and that the 3 dice rolls came out as 4, 6, 5. Then what we're looking at over here is the maximum of 4 minus delta 1, 6 minus delta 2, and 5 minus delta 3, right? So the rounding for each of the dice rolls gets applied to 4, 6, and 5. And in this case, because 6 is the maximum, 6 is the biggest one, it really does not matter the values of delta 1, delta 2, and delta 3. 6 is always going to be the biggest one, right? Delta is always between 0 and 1. It can never change who is going to be the maximum in this equation. 6 is always going to be the winner. So the maximum is just whatever is in this middle term. It's 6 minus delta 2, right? That is going to be the maximum no matter what. And so based on this example, you might hope that when you do the maximum of this whole combination of x's and deltas, really what you get is the maximum of just all the x's minus the delta of the winner. So whichever x is the biggest, that will be the maximum over here. And then this little delta is sort of along for the ride. It's whichever delta came with the maximum x value. You might question, is this true or not based on the example we saw? It's sort of true. We're going to see in a minute it's not exactly true, but it's good enough for now. And if you believe this, then you can take the average inside. So you do the average of the x's, you do the average of the delta. And like we said before, delta is between 0 and 1. The average of the delta is a half. So you get the average of the x's minus a half. This is equal to n times m over m plus 1. You just rearrange the equation and you get that two-term approximation that we wanted to prove. Great. All right, the only problem is it's not exactly true. And we're going to see when we do the third term that when you pull the deltas out, it doesn't always pull out as cleanly with one delta coming out like we saw before. So when we do the third term, you're going to see multiple deltas combining to give some nastiness. Let's see what that looks like. Okay, so here's the three-term approximation, and it really is building on what we did before. We're going to take m over m plus 1 times n plus a half, and we're going to see where this minus m over 12n comes from. And it really starts with this x minus delta is exactly the same as the nu like we had before. And now we're going to find the truth of exactly what happens comparing the maximum of the x's with the deltas to the max of the x's without the deltas. And it's not quite as simple as we saw before. So in the last example we had 4, 6, and 5, and it really was true in that example that the maximum is exactly just whatever is coming from that middle delta. So it's 6 minus, and the delta you get is exactly that delta 2. But here's a more complicated example. If the dice rolls come out as 6, 6, 5, then now when you do the maximum, you have 6 minus delta on that list twice. You have 6 minus delta 1 from the first term and 6 minus delta 2 from the second term. So again, 6 is definitely going to be the maximum, but which one we take, is it going to be 6 minus delta 1 or 6 minus delta 2, is going to depend on whichever is bigger, right? If 6 minus delta 1 is bigger, we get 6 minus delta 1. If 6 minus delta 2 is bigger, then we get 6 minus delta 2. So we always get a 6, but the deltas are going to combine from delta 1 and delta 2. And so in this situation, we're going to get the minimum of delta 1 and delta 2. So comparing example 1 to example 2, you see that because there was a tie for first place in example 2, we ended up with a minimum of two things, the minimum of delta 1 and delta 2. Because there was no tie in example 1, we just had a single delta 2 sitting on its own. And this is the little trick that is going to give us that third term in the approximation. In this case, when we take the average of these sides, the average of delta 2 on its own, and the average of the minimum of delta 1 and delta 2, well, the average of delta 2 on its own is a half. What is the average of the minimum of delta 1 and delta 2? Fortunately, we did that already way back in the first term. That is going to be a third. And that's because, we have 3 segments. We're picking one of them for the minimum. That's the k equals 1, m equals 3 situation we did a while ago. You subtract a third. So this is what's really going on. Sometimes you have to subtract a half for the rounding. Sometimes you have to subtract a third for the rounding. And it's this weird combination between them that is going to give the third and fourth and so on terms. So in general, what's going to happen, we're going to have the maximum of x1 minus delta 1 all the way up to xm minus delta m. That is going to be equal to the maximum of x1 to xm minus, and then you're going to have a bunch of deltas over there. The number you have is what I call n maxers, where n maxers is the number of dice rolls that are tied for the maximum. So if it's one dice roll on its own, that's going to be a single delta. That's going to be a half, like in term 2. But it could be 2 dice rolls that would give a third, or 3 dice rolls that would give a quarter, and so on. And it really just depends on this number, num maxers. So by what we did before, that expected value is 1 over 1 plus the number of n maxers, right? The number of dice rolls that are tied, you get 1 over 1 plus that amount. That's exactly like the expected value of uniforms we did earlier. And now we're in good shape. The left-hand side of this equation is exactly what we want with the nu's. Pull the factor of n out, you get m over m plus 1 times n. Rearrange the equation for what we want. and we find that the average maximum of a dice roll is m over m plus 1 times n plus this expected value. It's exactly equal to this. This is an exact formula. And we can expand this out into probabilities. So there's a probability there's one dice roll that is the maximum. There's a probability there's two dice rolls that are the maximum, and so on and so on. You could have up to m dice rolls tied for the maximum. That's when you roll the dice and they're all exactly equal. So that is very rare, but it does happen. That's somewhere deep in the tail of our sum. And the approximation we had before was basically saying, oh, it's a 100% chance that n maxers equals 1. Just ignore all the terms other than this a half. We can get a more accurate approximation by calculating how big this error is. So let me simplify this a bit. Instead of doing a half when n equals 1, and then a third when n equals 2, and so on, let me always do a half, and then I'll correct the sum based on what n is. I claim that this formula is exactly equal to the same thing, where you always add on a half, and then you do a third minus a half when n maxers equals 2. So you can think about this as, look, we're always going to do a half, and then we're going to fix the formula. If n equals 2, we're going to add on a third minus a half, and that minus a half will cancel with the first a half, and we'll get back to a third, which is what we had before. Algebraically, this is everybody's favorite math trick where you add and subtract 0. In this case, 0 is equal to 1 minus the sum of all the probabilities. And the nice thing about doing this is we've isolated that plus 1/2 as its own term. So now it's always plus 1/2, and then we have 1/6 times the probability that the number of maxers equals 2. There's higher order terms. That's going to be like something involving the probability that the number of maxers is 3 or 4 or so on. Unfortunately for us, we can calculate what these are. So we will show that this probability, that there's a coincidence of 2 dice tied for the maximum, will show that it's m over 2n plus smaller terms. So terms that are size 1 over n squared for large values of n. This big O notation, I remember finding it very scary, but in this situation, it literally just means, look, I was too lazy to write out all the terms, and I've combined all the terms that start with 1 over n squared. I've combined them into one thing I call the big O term. That's like junk I don't care about because it's so much smaller than the m over 2n term. So you'll see when we do expansions where this comes from, and it really is just like lazy bookkeeping, right? Just stop at the numbers that are big. Don't write down the really small numbers. They don't affect our final answer. They are so small, we don't care about them. That's what the big O 1 over n squared means. At the same time, we're also going to show that all the probabilities for having 3 or more things tied for the number of maxers, that is also very small. So you sort of need a double coincidence to happen with the dice. Like you need 3 dice to all be equal to the same value, and that has chance 1 over n squared to happen as well. These will be beyond the level that we will do. So we're going to take this, the probability of n maxers equals 2 is m over n. If you plug that into the formula that we have, then you get exactly this minus m over 12n, which is our third term. So this is our 3-term approximation, and it really is just accounting for the probability that the 2 dice that are the maximum are tied for the maximum. And if you include that, you get this 1 over 6 correction. The probability is m over 2n, and that combines to give this m over 12n correction as the third term in our formula. All right, the last thing we got to do is prove this. Why is the probability m over 2n? And it involves the birthday paradox. Okay, so this is what we want to show. Let's pretend we had no idea what the answer was. How would we calculate this? And now we're in a situation where we actually don't care about the values on the dice anymore. We just care about how many dice are tied for the maximum. Like this is a question you can ask. You just roll the dice, you see how many are tied for the maximum value. It does not matter if that maximum is 20 or if it's 10 or if it's 5. The value doesn't matter, just the number of things that are tied for the maximum matters. And this is a lot like everybody's favorite probability problem, which is the birthday paradox. So in the birthday paradox, you can imagine n is the number of days in a year, and you have m people who are in a room, and you're asking what is the chance that there's coincidences where people have the same birthday? And that's exactly the same as us, except we're doing dice and number of dice rolled. So every single dice, you can think of what it comes out as, that's its like birthday. And then we're asking, what's the chance when we roll m dice that we have this coincidence that 2 dice are exactly the same value? So it really is mathematically exactly the same as the birthday problem. And the way you calculate the birthday problem is you do the following. So we're going to first calculate the probability that all the dice are different, or equivalently in the birthday setup, all the people in the room have different birthdays. And the way you do that is you argue sequentially. So imagine people walk into the room one by one. When the first person walks into the room, of course, that person has a 100% chance of having a different birthday than everybody else in the room. There's only one person in the room. So the first person has a 100% chance of their birthday being different than everybody else's in the room. Then when the second person walks into the room, they have a 1 minus 1 over n chance of having a different birthday than everybody else in the room. And the reason is there's already one person in the room. There's a 1 over n chance those two people share a birthday. So when the second person walks in, there's one person's birthday to compare to. As long as we don't hit that person's birthday exactly, then we're good and we have different birthdays. Now, when the third person walks in, there's two people's birthdays. There's already two people in the room. So when the third person walks in, there's a 2 out of n chance of sharing a birthday and a 1 minus 2 out of n chance that the third person has also a unique birthday. So every time somebody walks in the room, you get this extra factor of 1 minus something over n, where something is the number of people that are in the room. And if you multiply this all out all the way up to the mth person, when the mth person walks in the room, there's m minus 1 people in the room. So there's a 1 minus m minus 1 over n chance that the mth person will also have no birthday in common with everybody. And if you multiply all these things together, that's the probability that in the birthday paradox, all the birthdays of the people in the room are all different. And for us, it's the same thing, but it's dice. So this is the chance of rolling our n-sided dice and having them all come out to all different outcomes. It's exactly that probability up there. And the nice thing is you can expand this out and see what is it in terms of n, right? So the first term in the expansion will be 1. You have a factor of 1 in every single term. Those all multiply together to give 1. And then you have, in the expansion, you have terms that have a 1 over n in front. And every bracket contributes exactly one term with a 1 over n. So a minus 1 over n, a minus 2 over n, all the way up to a minus m minus 1 over n. So you can imagine multiplying all these brackets out, right? You have all these m brackets, you multiply them all out, and you get a whole soup of terms, but these are the only terms that are something over n. And all the other terms will be things that involve n squared and so on. So now notice that you have here the sum, minus 1, minus 2, all the way up to minus m minus 1. That is m times m minus 1 over 2n. It's the sum of the numbers 1 to m minus 1. Very nice formula. It happens to be the same as m choose 2. This is the number of pairs of people. So if you have m people in a room, m times m minus 1 over 2 is the number of pairs of people that are there. This is what makes the birthday paradox the birthday paradox. People often forget that it's really the pairs of the number of people that matter, not the number of people themselves. So people are often surprised that it depends on like m squared rather than just m. But in any case, for us, we have 1 minus m times m minus 1 over 2n. And the next order term is everything and everything else. Those will all be 1 over n squared and smaller terms. So when you do the expansion, you're going to get all these super teeny tiny terms that are like 1 over n squared and smaller. We're going to ignore those terms. We're thinking of n, the number of sides of the dice, as very large compared to m, the number of dice we're rolling. All right, so that's the probability that all the dice work out to be different numbers. What's the probability that there is one coincidence? And by one coincidence, I mean of the m dice that we roll, that there's exactly 2 dice that are equal in value. Well, this is another one you can work out very similar to the birthday paradox situation. First, let's choose amongst all the dice, which 2 of them are going to be the ones that are the same value. So that's exactly the number of pairs of all these dice. And that is m times m minus 1 divided by 2. That's the number of ways you can choose which 2 dice you're going to have them be equal. And the chance of them being equal is 1 over n. So if you have a fixed set of 2 dice, like these 2 dice, the chance that they roll the same value is 1 over n. So that's all the different ways of the m dice you have to pick 2 of them and make them come out as equal values. Then, after these dice are set up, you want all the rest of the dice to work out to different numbers. And that's exactly what we saw for the all different situation. You need the next dice to walk in the room that needs to be different than the dice after that, and so on. They all need to work out to different things. You got to make sure all those extra dice are different numbers, are not equal to that one coincidence situation. If they were equal, you would have more than one coincidence. We're calculating the probability that there's exactly one coincidence over here. And once again, when you expand this, you find that the only term that has a 1 over n dependence is that first term, m times n minus 1 over 2n. All the other terms are 1 over n squared. They're all teeny tiny terms that are so small, we're going to just round them off and say they're rounding errors. We're not going to keep track of them. So now by thinking of this as the birthday paradox, we've calculated the probability all the dice are different, and we've calculated the probability that there's exactly one coincidence. And you can see from these 2 terms that they add up to almost 100%. And that's because the probability of 2 or more coincidences must be so small that it was in our rounding errors, right? The chance of all different and the chance of one coincidence, they add up to 1, except for all the teeny tiny rounding errors. And therefore, 2 or more coincidences is also a teeny tiny rounding error. Last but not least, we don't actually care about the coincidences amongst the whole population. We care about the coincidence for only the maximum dice, the n maxers. So what is the probability that there's 2 dice that are tied for the maximum? Well, you need a coincidence, and then you need the coincidence to happen exactly for the largest dice. And there's m minus 1 dice sort of values in the pool. That's because there's m dice, but 2 of them are equal. So there's m-1 unique values, and all of them are equally likely to be the maximum. So again, by a symmetry argument, to get n maxers equals 2, you need exactly 1 coincidence somewhere in the population, and then you need a 1 over m-1 chance of that coincidence happening exactly on the largest dice, on the maximum dice. Of course, there are other ways, but the other ways all involve like 2 or more coincidences happening, and that is super small probability. It's order 1 over n squared. So finally, if you take what we did, so the probability of one coincidence is m times m-1 over 2n, the probability of n maxers equals 2 is that divided by m-1, while the factors of n-1 perfectly cancel out, and you get the answer we wanted, which was m over 2n, plus, super teeny tiny errors that we are not keeping track of. Okay, and that finishes the last technical little thing we have to do. If you made it this far into the video, let me give you a bonus 4th term for free. So in the video, we proved the first 3 terms, m over m plus 1 times n plus a half minus m over 12n. And the 4th term, I'll tell you what it is. Are you ready? It's 0. It's 0 over n squared. And you might scratch your head and say, what do you mean the 4th term is 0? You can't just add on 0 and say you've given me a free 4th term. You haven't given me anything. But really what I mean is that if you calculate the error, it's 1 over n cubed. So if you do this series expansion and you keep calculating more and more accurate things, in the main video, we calculated up to 1 over n, but you could calculate up to 1 over n squared, you will find that the term in front of n squared is 0. So it's 0 over n squared, and all the other terms are 1 over n cubed and smaller. And that's partially why when I showed the graph way back in the introduction, the errors were so teeny tiny, because the errors are actually smaller than you expect. I don't actually have a good intuition of why this term is 0, other than you can crank it out and it works out to 0 in some complicated way. But if you want to work it out and have a nice proof of why it's 0, please let me know in the comments. And if you've made it this far, you should probably subscribe so you can get more probability ninja proofs as they come out.